I will begin with a word of prayer. Heavenly Father, we thank you for this day. I thank you for the students, and we thank you for homework, which is fun. Help us to enjoy it every week, and help us to enjoy this class and just to learn a little bit more about your creation together, Lord. In your name I pray. Amen. All right, so if that's not you, I'm sorry, but you made some bad life choices to be in this class. Sorry. No. I feel your pain. Once upon a time, I had to take this course called Graduate Physics Laboratory, which I was wholly disinterested in. It was singularly the worst experience of my life, academically speaking. So, Theorem, I mean, it was a legit course and everything. It's just I wasn't interested. If G is a group, all right, G is a group, and A is in G with the order of A equals to N, and K is a natural number, then here's the punchline. The cyclic subgroup generated by A to the power K is equal to the cyclic subgroup what? GCD of N comma K, and the order of A to the power K is equal to N divided by the GCD of N and K. All right, so last time in the help session, I got all the way up through corollary 2.6.12. What did corollary 2.6.12 get to say, for those of you who remember? Corollary 2.6.12 said that if the order of A is n, and if a to the k is equal to the identity, then k must be a multiple of n, right? So we had that was our last result that we got in the help session. I'm going to try to prove this thing here, which is theorem. What is this one? It is theorem 2.6.13 on page 65 of my notes. So I'm going to try to prove this somewhat carefully. Here we go. Proof. Assume G is a group. And A is an element of the group, all right, with the order of A equals to N. Also, K is some natural number, all right? We're going to let D equal to the GCD of N and K. We know that exists because, well, we've studied integers, right? Now, if D is the greatest common divisor of N and K, in particular, D is a what? That means D is a divisor of both N and K. What's that mean? There exists, let's see here, for the purposes of my proof, I need to notice that there exists a Z in the integers such that K is equal to ZD. All right. Now, what we're trying to do right now is to prove the equality of two sets. So what's our game plan? So I'm gonna work on this kind of subset to start with, right? I'm gonna say let X be an element of the cyclic subgroup of G generated by A to the power K. What's that mean? That means there exists like an integer L such that what? X is equal to a to the k to the L. Right? But then all we got to do is use laws of exponents here, right? We know that you can see it right above. K is equal to ZD, right? So just take this K and put that in there instead. And what does that give us? That gives us a to the ZD to the L, or more to the point, a to the D raised to the ZL power by laws of exponents. What's the significance of that? Well, in my current notation, notice that this is nothing more than a to the D, right? That's the cyclic subgroup generated by a to the greatest common divisor of n and k, which then says that x is an element of what? X is an element of a to the D. And that completes the proof that, consequently, what have we shown? We've shown that a to the power k, that cyclic subgroup, is a subset of a to the GCD. GCD of nk. That's half of it, right? Now the other direction. We're going to show this kind of subset. So let's let, well, here, I'll use the letters I used in the notes just to, oh, I used X again. Wait a minute, no, I used W. Let W be an element of the cyclic subgroup generated by a to the power GCD of n comma k. All right. Again, I'm going to call the GCD D again. D equal to the GCD of n comma k. All right. So, and note, and note, there exists, let's see here, u in the integers such that W is equal to what? A to the D raised to the U power by the definition of cyclic subgroup generated by A to the power D. All right, great. However, by Bezout's identity, by Bezout, there exists P comma Q in Z such that what? Well, Pn plus Qk equal to what? D. Also, before I write the next string of inequalities, recall what's a to the power n? It's e. We're assuming that, right? So that gives us the following string of equalities. I'll write down next. So W equals to a to the D U, right? Which is equal to a to the what? Pn plus Qk times U, because that's what D is, which we can rewrite as a to the n to the Pu times a to the Qku, right? Great. But a to the n, that's the identity, right? And so what we have is a to the Qku. What am I trying to do? I mean, that's essentially it, right? Just rewrite that. Laws of exponents again. This is a to the Qu, right? Raised to the k. Oh, I'm sorry. Is that what I want? No. Other way around, right? I want a to the k raised to the Qu power. That makes it manifestly clear that is an element of what? That's an element of the cyclic subgroup generated by a to the k. See, because a to the k to an integer power, this is an element of this guy, right? Therefore, what? Therefore, a to the GCD of nk is a subset of a to the k, cyclic subgroup generated by a to the k. So we've shown the inclusion both ways, so that establishes the equality of those sets, right? It remains to show what? It remains to show the order of a to the k. So observe that a to the, now check this is a kind of sneaky step, a to the d to the n over d. Now why can I, what is n over d equal to? In my current lingo, n over d is equal to, wait a minute, oh I don't know. Yeah, I mean, I know that G is the greatest common divisor of, I mean, there has to be some other, like Z2, right? N is equal to what? Say Z2 times D, right? Because it's, D is a common divisor of both N and K, right? So there has to be some Z2 like that. So it follows that N over D is an integer is my point, right? So it makes sense to say a to the d to the n over d, because n over d is by assumption here an integer. I can raise it to this power. But this is equal to what? Well, this is equal to a to the n, right? Which is, of course, e. Therefore, the order of, oh, shnikes, I lost track of my thing. Well, therefore, the order of a to the d is less than or equal to n over d. Fine. Right, stick with me here. There's something sneaky going on. If 0 less than I less than n over d, then what? Then certainly di is less than n. All right, I'll buy that. So a to the di is what? Well, a to the d to the I, which is a to the, a to the di, is not equal to e. How do I know that? Right, because the order of a is n, right? Exactly. Thank you. And what's that say? Thus, the order of a to the d is equal to what? N over d, because we showed it's at most n over d and it can't be less than it, right? Great. Still not what I want, right? I'm trying to get this. How am I going to get to that, right? Still don't have it. All right. Corollary 2.6.11 assures us that the order of an element is the same of the order of the cyclic subgroup it generates, right? So notice that the order of a to the d is equal to the order of a to the what? GCD of n comma k. I mean, that is d, right? In our current notation. All right. But that's equal to what? Apparently that's equal to n over d, right? But what else do we know? Also, the order of a to the k is equal to the order of the cyclic subgroup generated by a to the k. And what did we already prove? Oh, we already proved that this and that set are the same set, right? Therefore what? The order of a to the k is equal to n over d, which, by the way, is n over GCD of n comma k. So there you go. That is a proof of theorem 2.6.13. Really, no step I made here was that difficult, right? It's just a matter of taking it step by step, calmly, and do it. Corollary to this theorem, it's a corollary, 2.6.14. It says that if the order of A is equal to n, then the cyclic subgroup generated by a to the power I is equal to the cyclic subgroup of a to the power j, if and only if the GCD of n comma I is equal to the GCD of n comma j. So it's a corollary to the theorem, right? Because all you got to do is, basically notice that, I mean, you see the proof? What's the proof look like? Something like this, right? A to the I is equal to a to the GCD of n comma I, right? But we're assuming that the GCD of ni is equal to the GCD of nj, right? Right? Which is by theorem I just proved equal to a to the j, yeah? Now, what I just did was actually this part of the proof, because I'm assuming what? Assume the GCD of ni is equal to the GCD of n comma j. If you make that assumption, then this shows you that the cyclic subgroup generated by a to the power I is equal to the cyclic subgroup generated by a to the power j. How do we reverse this chain of logic? So the other direction of the proof, we should what? We should assume that a to the power I is equal to the cyclic subgroup of a to the power j. Our goal is then to show what? That the greatest common divisor of n with I and the greatest common divisor of n with j are equal. How do we get that? Well, this implies, among other things, that the order of ai is equal to the order of a to the power j, right? Do we have anything in this theorem we could use? How about this? Oh, check it out. The order of a to the power k is n over the GCD of n comma k, right? Let's use that with k equal to I and k equals to j. See what happens. So I've already forgot it because I'm all the way over here. But I think it was n over GCD of n comma I equals to n over GCD of n comma j. And so therefore, GCD of n comma I equals GCD of n comma j, and there you have it. And again, I'm skipping some words, as I will sometimes do in class, but proper etiquette, mathematical etiquette would say things like, by theorem, I need to get glasses, 2.6.13, you make that step, right? Does that make sense? Now, this is a terribly useful corollary because it gives you all kinds of insight as to how to construct generators in a cyclic group, right? Like if you want to find two different generators for a cyclic group, then if they're both powers of a particular element, the only way they can both be generators is, if they're in the same way related to n. If they're both relatively prime to n, for example, they could both serve as generators, right? But we'll get more into examples here shortly. But next corollary, 2.6.15 says that if A is a cyclic group of order n, then G is equal to a to the power k if and only if what? If only if the GCD of k and n is equal to 1. Now, I think I mentioned this in the help session, but now we've actually proved it. All right? So this is almost immediate from the previous corollary, right? I guess I should write the proof down. So here's the first thing. We have A equals a to the k, right? That implies, by the previous corollary, what? The greatest common divisor of n and 1 is equal to the greatest common divisor of n and k, right? What's the greatest common divisor of n and 1? One, right? So there's that direction. How about the other direction? Suppose that the greatest common divisor of k and n is equal to 1. Then, this is stupid. I'm sorry. Then GCD of n1 is equal to 1 is equal to GCD. It's almost the same stupid argument, right? Which implies that a to the power 1 is equal to a to the power k by the previous corollary. And this is G. By assumption. A is a generator. All right. That's corollary 15. Corollary 16, now the corollary 15 was for an arbitrary cyclic group written in multiplicative notation, right? A straightforward application of this is just to the integers mod n. Sorry, I forget. Stupid. I should like forbid myself from writing in a certain region here. Here, I'll make it a color I can't ignore. I will not write below this line. It is forbidden. All right, this is no man's land. Appropriate color. Let's see here. Okay. I stand by that joke. I can still tell it this decade. Maybe not the next decade. I don't know. We're just an election cycle or two from me going to jail for that joke. I don't know. Let's see here. Oh yes, Zn. So 16, corollary 2.6.16 says that k is equal to Zn if and only if the greatest common divisor of n and k is equal to 1. In other words, the generators for Zn are precisely those numbers which are relatively prime to n. We have a name for those, right? In other words, if and only if k is an element of the units, right? The group of units of Zn. Okay. So I think that's it for lecture 6 in terms of the major results in there, if I'm not remembering wrong. That brings us to lecture 7. And lecture 7 begins with this cavalcade of examples, which we should look at and appreciate together rather than me writing down. I could write them down, but it would eat a bunch of class time. So I'm going to project it and let you write them down. And or you could, of course, just summarize the examples. That's kind of more the point. Come on. Wake up, I say. Come on. You can do it. You can do it. So, I mean, by the way, this theorem is a pretty good example of a tough theorem that I might ask on a test, you know? That's kind of the edge of what is a reasonable test question. But, you know, if I do that, I'm allotting 25, 30% of your test time just for this problem, you know? Like, I think it takes 10, 15, 20 minutes to really write this out properly. But here's the corollaries we just went through. Here's an example. Well, this example is worth looking at here for a minute. Eventually, I will get my ducks in a row up here. Relaxing. So U14, what is U14? U14, it's got your 1, your 3, your 5, your 9, your 11, and your 13. All right. In fact, it is a cyclic group. You can show that 3 generates it. Like 3 to various powers mod 14 generate this list. 1, 3, 3 squared, 3 cubed, 3 to the 4th, 3 to the 5th. In fact, mod 14 are 1, 3, 9, 13, 11, and 5. Great. So that's everything. That means that, in fact, U14 is a cyclic group. Not every group of units is a cyclic group. This is kind of like, the structure of UN, it's varied. Eventually, I will come to a concise and sort of overarching description of what's going on there, but I'm not going to tell it to you because that's not the point right now. The point is for you to calculate for small n, try to wrestle with it for yourself and understand what UN looks like. So here it's cyclic, order 6. And so which 3 serves as a generator, right? So 3 to the k will also be a generator if k is what? If k is relatively prime to 6. What numbers are relatively prime to 6? You got your 1, 2 is out, 3 is out, 4 is out, 5. That's it. So that means that for a cyclic group of order 6, there are only 2 generators. I said 3 was 1. Apparently 3 to the 5th is the other. So 3 to the 5th being 5. So only 3 and 5 serve as generators for U14. That is the import of the theorems we just worked out. It's not at all obvious, without doing some calculation in here, that the other things wouldn't work, right? And you can be more abstract. You could say, suppose you had a cyclic group of order 8. You got your E, your A squared all the way out to a to the 7th, right? What other powers of A serve as generators for a cyclic group of order 8? So the question is, A to the K equals to A, cyclic subgroup generated, which K are relatively prime to 8? You got your 1, 2 is out, 3 is good, 4 is out, 5, 6 is out because it's got a 2 in it, 7. You got 4 generators for a cyclic group of order 8. A cubed, a to the 5th, a to the 7th. There you go. Yep.
How did you originally know to start
calculation. Yep. Tinkering. I mean, you can pick any power you like. Pick any number you like in a group that you think might be cyclic, and then look at powers, right? So it's either going to generate the whole thing, or it's going to generate some like subset of it, which is kind of suspiciously missing other things. And then you want to pick something that's not in the subset you generated, and see if that does everything. Something like that is a kind of a crude algorithm for us at the moment. All right, so examples. Let's keep going with our examples. If G is a cyclic subgroup of order 5, all right? So if I look at cyclic subgroup of A generated by a cyclic subgroup of A to the power k, what k will work if the order of the group is 5? Which numbers are relatively prime to 5? 5 is prime. Woohoo! 1, 2, 3, and 4, right? So for a group of prime order, there will be prime minus 1 generators, because that's how many relatively prime numbers there are to a prime. For 5, there are 4. For 7, there are 6. For 11, there are 10. For 13, there are 12. Yeah, I could go on, right? But at some point, my memory will... 37 is prime, right? For 37, there are 36. 41 prime? Okay, good. Yeah. Well, maybe. Let's see here. A to the 4th. Oh yeah, this is embarrassing. So apparently, when you use a squared, the order of the group drops to 4. Everything else has got 5 things in it, but I've redefined the group just for that one case. No, that is a typo. Yes, indeed, there is a missing. Thank you. A cubed at the end here. Yes, thank you. Because so that would be a to the 6th, which is a, but then a to the 4th, a squared to the 4th power would be a to the 8th, which mod 5, because we drop off the a to the 5th times a cubed, a to the 5th being e, drops us back. The next thing is a cubed, yes. Thank you. But you can see, once you correct my stupid typo, that a squared, a cubed, and a to the 4th all serve as generators for a cyclic subgroup, a cyclic group of order 5, right? Now, if we had a cyclic group of order 25, then some kind of more interesting things happen, yeah? I always forget to do this. You all are here, so it's just the internet suffering right now. It's okay. They've also got better instructors out there. So anyway, so you've got Z25. Well, okay, what's relatively prime to 25? What was that? Well, that's an interesting one. It would have been cool if it happened again, right? Curses. Wait a minute, which one of you is doing it? Got like a... what's that movie with the blood and the stage and the bucket of blood gets dropped? Yeah, it's like Carrie, except with projectors. Which one of you is the projector Carrie? That's right. Yeah. There's a. Is that count as a quote? I don't know. You're looking for quotes. No, I think there's like too much context to that. I don't think it's going to work. Anyway, so Z25. If you think about what's relatively prime to 25, certainly not multiples of 5. So like 0, 5, 10, 15, 20. Those are out. But I think otherwise you're okay, right? Like 1, 2, 3, 4, 6, 7, 8, 9, 11, 12, 13, 14, 16, 17, 18, 19, 21, 22, 23, 24. I mean, those are all relatively prime to 25, right? So yeah, like however that many is of them. But here's the interesting thing is there is a interesting subgroup that's generated by those ones that are not relatively prime as well, right? So if you look at the subgroup generated by 5, additively, you get 0, 5, 10, 15, 20. That's a subgroup of order 5, right? It's kind of interesting. What are the other generators of this? Well, that's a subgroup of order 5, right? It's a cyclic group of order 5, in fact. So what are the other generators? Anything non-zero in there is a generator, right? If it's a cyclic subgroup, if it's a cyclic group of order 5, then you have 4 generators. Anything non-identity will be a generator in a cyclic group of order 5. That's what we learned today already. That's true whether it's the whole of Z25 or whether it's this subgroup of Z25, which is itself a cyclic group. So apparently this subgroup of a cyclic group is itself cyclic. All right. Here's another example, that the 8th order group, right? If you look at a squared, you got your e squared, a to the 4th, a to the 6th, right? So this is a cyclic group of order 4. How many generators for a cyclic subgroup of order 4? What's in U4? Yeah, just 2 things, right? 1 and 3. So the original a squared is a generator, but also a squared to the 3rd power, which is a to the 6th, is a generator. Those are your 2 generators for that subgroup. There's also the subgroup of order 2, generated by a to the 4th. That just has one choice of generator because there's only one thing in the group of units mod 2, right? U2 has just got one thing in it. It's Bono. So, Bono? I'm sorry. Should I tell you it has glasses? I mean, what does it take for you to get to understand? Fine, I give up. No one's going to acknowledge this joke. I'll accept it. The cyclic subgroup generated by the identity is just the identity itself. So, I mean, so there's some features to these examples if you just start looking at them. For G itself, we have 4 choices of generators, again, because G is order 8. So U8 has 4 things in it, which means for a cyclic subgroup of order 8, there will be 4 generators. You give me 1, I can obtain the other 3 by just taking powers of that in the U4 powers. So if I start with A, I can either take the 3rd, the 5th, or the 7th power of A, and that will give me the other generators. If you started with A to the 5th, I could take the 3rd, the 5th, and the 7th powers of that to get the other 3 remaining. It doesn't matter which one you start with. Taking the non-identity powers in the group of units will generate the other generators. So here is Z20. What do you got in here? You got your group. Here's my group of units, mod 20. It's got these 1, 2, 3, 4, 5, 6, 8. Ocho? I don't know. I should learn these things. It's the future. So 8 things, right? And anyway, so the 2 generates the cyclic subgroup of order 10. 4 generates a cyclic subgroup of order 5. 5 generates a cyclic subgroup of order 4. 10 generates a cyclic subgroup of order 2. 0 generates the identity trivial group. These are my subgroups for Z20. And of course, any of these numbers has order 20, mod 20. In other words, you have to add this number to itself 20 times. Any of these numbers, you have to add to itself 20 times before you get back to 0 mod 20. That's because all of these have order 20 because they generate Z20. I'm trying to tell you a bunch of things that are, because I write these corollaries and these theorems, but they don't mean anything to you until I put numbers to them, right? So I'm hoping having this discussion helps kind of cement these ideas into place. They also give evidence for this beloved theorem of ours. And it's basically here are the points that are patterned. Patterns that you might notice is every subgroup of a cyclic group is cyclic. In fact, a subgroup of a cyclic group is cyclic. Every order of the subgroups we've seen has divided the order of the group. If you go back and look at it, we never had like a group of order 10 and, oh, look, a subgroup of order 7. You know? No, if it's a group of order 10, the subgroups either were order 2, order 5, or order 1. Order 10, it's the whole stupid thing, you know, but. And then finally, for each, now this is a little bit harder to see in the examples, but it's also borne out. For each divisor of the order of group, there is just one subgroup of that order. All right. So this is the so-called fundamental theorem of cyclic groups. Again, here's a careful statement of it. Let G be cyclic with generator A. If H is a subgroup of G, then H is cyclic. If G has order n, and H is a subgroup of G, and if the order of the subgroup is K, then K has to be a divisor of n. But it's better than that. If G has order n and K is a divisor of n, then there exists H, which is a cyclic subgroup. In particular, it's better than just that. You have a formula. Here's how you generate it, a to the power n over k. That will generate the unique subgroup of order n over k in G. Now, it's not emphasized in point 3, but part of point 3 is saying that every divisor of the order of the group, for every divisor of the order of the group in a cyclic group, there is a corresponding subgroup of that order, and here's how you generate it. For example, if I'm in Z20 and I want to, if I want to generate a subgroup of order 10, what do I use? I take 20 over 10, which is 2. So the cyclic subgroup in Z20 generated by 2 additively gives me a subgroup of order 10. 0, 2, 4, 6, 8, 10, 12, 14, 16, 18. That's a subgroup of order 10 in Z20. Now, sometimes you have to understand this theorem additively, of course, but yeah.
Back whenever you listen to the subgroups of Z20, I'm a little confused on why you picked those, not the ones that were in U20, but the ones, that's not all of the subgroups, right?
This is all of the subgroups for Z20, yeah, additively. Now, I don't know about subgroups of U20. That's another thing altogether. That may not even be cyclic. I don't know what U20 is. U20 is a different thing. But Z20 is a cyclic group. It's generated by 1 or 3 or 7 or 9 or 11 or 13 or 17 or 19. Any of these will do. I recommend 1. And here's the subgroup of order 10. This is the subgroup of order 5. This is the subgroup of order 4. This is the subgroup of order 2. And this is the subgroup of order 1.
So if you picked, like on the Z20, if you picked, tried to make 3 a generator, that would not be cyclic?
If you make 3 a generator of Z20, you get the whole thing.
Oh. Oh, okay.
Yeah. Okay. Now the proof is right here, and you should study it, right? Let me start. I'll do at least part of it today. To prove, 1, that a subgroup of a cyclic group is cyclic, well, if it's a subgroup of a cyclic group, that means it's formed by, a to the power k for some k in integer, right? So if you look at, well, first of all, so I'm going to assume that H is not the identity group to keep it, Okay, so if we have the identity, what's the identity to any power? It's the identity, right? So if it has just the identity, it's cyclic. Yay, we're done. The trivial group is cyclic. So suppose it's not the trivial group. In other words, suppose that H has a to the k, which is not equal to the identity, right? Then if you look at it, it also has a to the minus k. So if k happened to be negative, a to the minus k would be positive, right? Or vice versa. But the point is, it's got at least some positive powers of k appearing in H. So you can look at the set of all possible powers of A appearing in H. That's the set of all positive powers appearing in H. A to the k, where k is positive. And that's a what? A subset of natural numbers. So we can apply the well-ordering principle to pick a smallest member, and that will allow us to generate H. That will form a generator. That's what this proof says. So, basically lambda is the set of positive powers of elements of H, all right? So it has to have a smallest element by the well-ordering principle. Let T be that smallest element. I say that, in fact, H is going to be generated by a to the power T. And here's the proof. Well, a to the T is an element of H. So a to the T to the S has to be in H, because remember, we're assuming H is a subgroup, right? So it's closed under exponentiation, closed to the group operations. And so so this is a subset of H, right? On the other hand, if we have a to the k is in H, then by the division algorithm, we can pick Q and R, for which k is equal to Qt plus R, where R is between 0 and t not included, 0 included possibly, all right? And so a to the k is a to the Qt plus R, which is Q, a to the Qt times a to the R, which says that a to the R is a to the minus Qt times a to the k, great. But what else do we know? A to the t is in H implies that what? A to the minus Qt, which is this, is also in H. Thus, that and that are all in H. What's that say? If this is in H and that is in H, the product is in H, that means that a to the R is in H. So what does that force us to conclude about R? R is a power less than t, such that a to the power R, where R is positive, is found in H. By construction of t, R must be 0. Otherwise, a to the R would give it a power of a which has a smaller power than the chosen t. So R must be 0, but R being 0 is exactly what we want, because if R is equal to 0, then k is equal to the Qt, which is to say that a to the t, which is to say that a to the k is in the cyclic subgroup generated by a to the t. So that demonstrates, in fact, that a to the t does serve as a cyclic generator. Oh, shush. Hey, I'll call you back. It's for a good cause. That's I made Bill's ringtone the whistling flute from Kill Bill. You know, it just made sense. Just made sense. Where was I? In case you didn't recognize that, I mean, fairly how well versed you are in the soundtrack of Kill Bill Volume 2. But where's the Volume 1? I don't remember. Not Liberty approved, right? Is it Liberty approved? I don't know. I feel like no. No? Is the violence serving some larger moral, like, is there some lesson that we're trying to learn through the violence? I don't know. I don't know. So that proves then that the subgroup is cyclic. So since it has a generator which generates it, all right? So moving on here. There's a few more well, I tell you, I'll probably prove 2 and 3 tomorrow. And we have a few more results that I'm still working on here. But we have a page left. I'm now behind. I hope you guys are happy. All right. See ya.